Today's experimental math seminar speaker is Professor Christoph Koutschan, who will from Rickham Institute at Austria, will speak on Christol's conjecture. Please.
Okay, thank you very much, Doron, for inviting me to your beautiful seminar. So this talk is about joint work that I did with these three people, two of which you can see. The third one, I don't have a picture. So Youssef Abdelaziz is a joint PhD student that was supervised by me and by Jean-Marie Maillard, who you see on the right. And he just graduated a few weeks ago. And so the main topic of our joint work is on diagonals and their application in physics. So Jean-Marie, he is a physicist, he is working in theoretical physics. And so you see these papers that we wrote together, they all appeared in physics journals, in journal Physics A. And they all deal with diagonals. We studied different aspects of diagonals of rational functions.
Wow, so you're a physicist now. I know you're a biologist. You're also a physicist. Okay.
Anyway, so I will focus on the last paper here. This is on Christol's conjecture, and I will explain to you in a minute what it is about. But before, I would like to give some preliminaries and background. So this work is heavily based, of course, on Koutschan-Lustig theory, on coherent sheaf cohomology, and on Calabi-Yau manifolds. And I assume that you're familiar with these notions. Of course.
I hope it. You got me scared.
Yeah, I couldn't help to make this link to your talk, Doron, of this morning. So it is very fancy. This is the short version of this slide. Okay, now let's go into it. What is a diagonal? Let's assume we are given a rational function R in several variables, x1 up to xn. So we can write it as a fraction of two polynomials, a divided by b. So a and b are polynomials in these variables. And we further assume that b at the origin is non-zero, so that we can expand this rational function as a Taylor series in the origin. So the multi-Taylor series, if we expand with respect to all the variables around the origin, this gives us a multi-sum, so a series of this form. So we have n summations, we have here coefficients, and we have the powers in our variables. So now the diagonal of this rational function is the univariate power series, where we just pick the diagonal coefficients. So those where all these indices agree, R sub m, 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 and so on. So pictorially, this looks like this. Let's look at an example. So here is a very simple rational function in two variables. If we expand it as a Taylor series, it starts like this: 1 plus x plus y plus x squared, and so on. I use here the total degree ordering. But now if I order the terms in an array according to the powers of x and y, so you see here 1, x, y, x squared, 4x, y, and y squared, and so on, then the diagonal is given by these diagonal terms here. 1, 4, 22, 136, and so on. So this is a diagonal. What can we say about diagonals? There, I want to focus on two very important properties of diagonals. So if we define f of x to be a diagonal of a rational function, then this function f is what is called globally bounded. So what does that mean? If there are two integers, c and d, non-zero, such that if we scale this function, so we put the c inside and the d in front, we get a power series with integer coefficients. And in addition, we want to assume that this power series has a non-zero radius of convergence. So differently stated, If you look at the expansion, if you look at the power series expansion, the coefficients are rational numbers with denominators, and these denominators, they can only involve a finite number of prime factors. So that by putting these prime numbers or prime powers here with the x, they will disappear. So if you have a power series with rational coefficients and you find an infinite number of prime factors in their denominators, then this series is not globally bounded. Okay, so this is the first property. And the second property that, depending on what your background is, either very obvious or not so obvious, is that the diagonal of a rational function is always D-finite. And D-finite means that there exists a linear differential operator with polynomial coefficients that annihilates f. So f satisfies a linear differential equation with polynomial coefficients. And why this is so, we will see later. Okay, so this theorem goes in one direction. If f is a diagonal, then it is globally bounded and D-finite. Now we can ask about the converse, and we would not be the first to ask this question, but it was Christol who first asked this question, and he actually conjectured that the converse is also true. So every power series that is both globally bounded and D-finite can be written, can be expressed as the diagonal of a rational function. This is Christol's conjecture. It appeared first in a paper in 1986, so it's 34 years old, and still it is not settled, it is still open, widely open.
I have a question.
Yes.
Are the coefficients integer coefficients of the rational function, of the denominator and numerator?
It doesn't matter. So as long as it is globally bounded, it's fine. But so if it is globally bounded, then by this simple transformation, you can make integer coefficients. So you can assume we are talking about integer coefficients.
Okay, thank you.
Without loss of generality. Okay. So this conjecture is open, and what makes it really difficult is that it doesn't say anything about the number of variables that you need. So if we go back, we have seen a diagonal is defined for a rational function in any number of variables. And here we are talking about a univariate series, and the conjecture just says that there exists a rational function in whatever number of variables, 3, 4, 5 variables, whose diagonal is this function. But we don't know any bound on this number of variables. The only thing that we can say is that for sure we cannot settle this conjecture with 2 variable rational functions. So there are examples where it is known that you need at least 3 variables, but it's in particular not known whether 3 variables would always suffice or anything else. Okay, here is the original version of Christol's conjecture. Of course, it's in French. And basically what you see here is in this first, in this proposition, it states the properties of diagonals. So every diagonal has the following properties. I mean, yeah, so you can, even in English, you can understand this. These French words are almost the same. It is a solution of a linear differential equation. So this is this D-finite properties. It's a Picard-Fuchs equation. So he uses a little bit different vocabulary, but this is basically the properties that I stated. And then here in the bottom, you see the conjecture. Every series that satisfies these properties above is the diagonal of a rational function. And so here in the sentence before, he already mentions that he wants to test this conjecture with so-called hypergeometric functions. So let me tell, or of course, most of you know, let me recall what hypergeometric functions are. so as usual, I define this Pochhammer symbol as the rising factorial. A sub k is the product A times A plus 1 times A plus 2 and so on. K factors with A0 being defined as 1. And then the PFQ hypergeometric function is a function in one variable x that involves P plus Q parameters. So we have the top parameters, A1 up to AP, and we have Q bottom parameters, B1 to BQ. And then this is just defined as this univariate power series, where in this fraction we have the Pochhammers with the A parameters in the numerator and the B parameters, Pochhammers go in the denominator. And there is an additional K factorial here. So in the following, we will somehow, so note that this K factorial is nothing else than the Pochhammer 1 sub K. Then you have 1 times 2 times and so on up to K. So that in the following, we will often refer to B sub Q plus 1 as an additional parameter that is set to 1. Okay, and we want to exclude trivial cases. Trivial cases occur when one of these parameters is a negative integer, 0 or a negative integer. So what happens if one of the A's is 0 or negative? Then this sum is terminating. So look at the Pochhammer. If this A is negative, then as soon as K is greater than or equal to A, then in this product you get a factor 0 and the whole thing is 0. So then what you get is a polynomial in X. If one of the B's is 0, this is even worse. Then in the denominator you have a 0, and we don't like division by 0, so then this thing is not defined. So in the following, I will always exclude these kind of trivial cases. Okay, though it has to be noted that hypergeometric functions are always D-finite. So the most prominent example is the classical Gauss hypergeometric function, where the parameter P is 2 and Q is 1. So 2f1 so has 3 parameters and X, and it satisfies this so-called Euler's differential equation. So you see it's a linear differential equation of order 2, and the coefficients are polynomials in X. Okay, and also for all the other P and Q, such hypergeometric functions satisfy a linear differential equation, then of higher order, and this is classical knowledge. So these functions, they provide a natural testing ground for Christol's conjecture because they are hypergeometric. Because they are D-finite, and it is very easy to decide whether they are globally bounded or not. So we can, by looking at hypergeometric functions, we can generate plenty of examples of functions that are both D-finite and globally bounded, and hence by Christol's conjecture should be diagonals of rational functions. However, we cannot work with the general PFQ for the following reason. So if Q is less than P minus 1, so that means if we have much fewer Pochhammers in the denominator than in the numerator, then this series has radius of convergence 0, because then these coefficients, they grow way too fast. So it's like some K factorial times X to the K. So these are not interesting for us. Similarly, if Q is greater than P minus 1.
It still makes sense as a formal power series.
Of course, it's a perfect formal power series, but for this condition that we impose, this globally bounded.
For the globally bounded, it
says that we want to have a non-zero radius of convergence. So that's why we are not interested in these cases. And similarly, if the other way around, if we have more Pochhammers in the bottom than on the top, then you can imagine that here we get a lot of stuff. And in particular, as we go to infinity, we get a lot of prime factors that cannot be canceled by the Pochhammers in the numerator. So then again, the series is not globally bounded. Not because of the radius of convergence, but because of the property of having only finitely many prime numbers in the denominator. So the only interesting cases for which Christol's conjecture applies is if Q equals P minus 1. So we are in the following, we are only considering hypergeometric functions of the form PF P minus 1. Okay, so now as a motivation, let me state the main result. We look at a particular hypergeometric function, and why we look particularly at this one. Of course, at this moment, this is completely obscure, but it will be explained and enlightened.
It's an infinite family. It's not just one, right?
Yes, it's a family, a parameterized family. Yes, that's true. And so we get that this is the diagonal of a rational function, and here is the rational function, again involving these parameters a and b. So if you put a and b to be concrete integers, then this is indeed a rational function. And okay, so this is somehow the rabbit out of the hat, and you may now ask, okay, why, how the hell you can get up with such a complicated rational function? And I hope that this is hopefully enough motivation to listen, because I will explain it, and actually you will see that there's not so much magic behind this. Okay, so let's start slowly. We need a few ingredients to argue all this stuff. Let me introduce the Hadamard product. This is when you deal with diagonals, this is an important operation that we can employ for different purposes. So if we have given two power series, f of x and g of x, we define the Hadamard product as the coefficient-wise product. So we just take the coefficients alpha n and beta n, we multiply them, and we define a new univariate power series. So this is usually called the Hadamard product. And so note that diagonals are closed under this operation, under this Hadamard product operation, in the sense that if you have two series that are diagonals of rational functions, then also their Hadamard product will be a diagonal of a rational function. And actually, this is very easy to see. So let me give you the proof via an example. So let f of x be the diagonal of some capital F in some number of variables, and g of x be the diagonal of another rational function, g, capital G. Then the Hadamard product of f times g is the diagonal of the usual product of capital F times capital G, but where we use distinct sets of variables. And actually, if you look at what happens here at this product, I mean, you can imagine it on univariate series. If you have f of x, if you look here, if you take f of x and you take g of y and you multiply them, and then you take the diagonal, on the diagonal you will exactly find the products of an times alpha n times beta n, and the same happens with several variables. Okay, so if you think about this for a minute, it is quite obvious. So this is the Hadamard product. Okay, the next notion we need is the height. So what is this? Let f of x be a hypergeometric function of the type pf p minus 1. So we have these parameters. And as I mentioned before, let's include this hidden k factorial in the form of one additional parameter bp that is 1. Okay, so then we have the same number of a's and the same number of b's. And so we define the height to be the difference of the number of b's that are integers minus the number of a's that are integers. Okay, So the height is number of integral b's minus the number of integral a's. And anyway, I wanted to remind you that everything that follows, we assume that these parameters of our hypergeometric functions, they are always rational numbers.
Is it a new concept or a new one? Or it's already existed before?
This height?
Yeah.
No, this was not introduced by us. This is classical. I mean, you can find it in I think in Beukers and Christol and so on. Okay, so anyway, so this is independent of this definition that these parameters are always assumed to be rational numbers. And yeah, so this was the definition of height. I will give, okay, let me just, so here we have an example. So this hypergeometric function, we look at the number of integral b's, and we have to recall that there is one more one that we don't see, that we don't denote, because they are normalized in a way that this last b is 1, so one doesn't denote it. So we have 3 integers here. We have 0 integers here. 3 minus 0 is 3. So this has height 3. Okay, so this is the concept of height. And now, using this concept, we can formulate 2 theorems. They are due to Christol. So if we have a p minus 1 hypergeometric function that has height 1, then the following holds. This hypergeometric function is globally bounded if and only if it is algebraic. So for such a hypergeometric function, globally bounded and algebraic, these 2 notions are equivalent. So this is the first theorem, and I will use it in the next slide. And also important is this one. If a function, if a hypergeometric function can be decomposed as the Hadamard product of, so we assume that it has height h. So h denotes the height of this function, of this hypergeometric function f. And if we can compose it in h globally bounded series of height 1, then f is the diagonal of a rational function. And actually this I demonstrate in the example on the next slide. So we have seen this one has height 3. So if I'm able to decompose it into 3 series of height 1, then it is the diagonal of a rational function. So how can I decompose it as the Hadamard product of 3 hypergeometric functions of height 1? Well, since the Hadamard product is the coefficient-wise product, and since these parameters just tell me that in the coefficients I multiply the Pochhammers 1/3 k, 1/3 sub k, 1/3 sub k in the numerator, and 1 sub k to the power 3 in the denominator, it is easy to decompose this as a Hadamard product of 3 series because I just have to partition the set of parameters. So so in each of the 3 factors, I put 1 1/3 in the numerator and 1 in the denominator, which is not denoted because it is never denoted. And that's why I can write this 3f2 as the Hadamard product of 3 times the same 1f0 function. Okay, it's just a set decomposition of the parameters for the Hadamard product. And so obviously these functions, they have height 1 because they have 1 non-visible integral parameter b and 0 integral parameter a. Okay, so I hope it is clear why we can write it as a Hadamard product like this. Now, how can we see that this is now a diagonal of a rational function? Well, we can observe that this 1f0 is a particularly easy hypergeometric function because just by the binomial theorem, it is a algebraic function. It is 1 minus x to the power minus 1/3. So this is an algebraic function. Now, using that the diagonals are closed under Hadamard product, we can now say the diagonal of this function f, since I can write f as the Hadamard product of these three guys, it is the diagonal of the usual product of these three functions where I replace the variable x by different variables. Okay? So, but we are not yet there. So now I have shown that this is the diagonal of an algebraic function. I claim that this is the diagonal of a rational function. So how does that come? For this, I have to invoke two classical theorems. The most classical one is the theorem by Fürstenberg. And he proved that for a univariate algebraic power series, f of x, it is always the case that that one can write this as the diagonal of a rational function in two variables. Every algebraic function is the diagonal of a bivariate rational function. Okay, here we have an algebraic function in three variables, so we need a generalization to many variables. This is due to Denef and Lipschitz, and they proved that any power series in n variables that is algebraic is the diagonal of a rational function in two n variables. So you have to double the number of variables, and then your algebraic function can be written as the diagonal of a rational function.
Do there exist algorithms to implement it?
Yes, and I even will show an example where I execute this algorithm. Okay, good. So then by this theorem, we know that this f is the diagonal of a rational function in 6 variables. Okay, so now let's see which examples of hypergeometric functions could be potentially interesting in the context of Christol's conjecture. So let's look at the somehow simplest non-trivial case. Let's look at 2f1 functions, and let's see whether we can get interesting examples that either, well, I mean, the hope would be that one finds a counterexample, right? Okay. So what is the situation for 2f1 functions? And actually 2f1 functions are not interesting because every globally bounded 2f1 hypergeometric function is the diagonal of a rational function. So if we restrict to this class, then somehow Christol's conjecture is proven for this special case. Let me elaborate a little bit how we can see this. So for example, let us consider that the two top parameters a and b are integers. Now there are two cases for the parameter c. Let's assume c is not an integer. Then the 2f1 function is not globally bounded, so this case is anyway not interesting for us, since we want to assume that the function is globally bounded. But if c is an integer, then it can be globally bounded, provided that these inequalities hold. So again, you have to consider that we have a sub k, b sub k Pochhammers in the numerator, and a c sub k and k factorial in the denominator, and we have to make sure that all the prime numbers that appear in the denominator somehow get cancelled. And that's why, so the a should cancel with the k factorial, and the b sub k should cancel all the prime numbers that appear from the c sub k Pochhammer, and this happens if b is greater than or equal than c. So if these conditions hold, then actually we can simplify these Pochhammers. There's a lot of cancellation going on, and what is left is just a polynomial in k. And so if we have an infinite series, polynomial in k times x to the k, then we know that this sum will give us a rational function. And of course, trivially, a rational function is a diagonal of a rational function. So also for this case, it is proven. Now let's look at the case where a and b are both non-integers, are both rational numbers that are not integral. Again, we make the case distinction for c. If c is an integer, then we get a 2f1 function of height 2. And this can be written as similar what we did before, like here. We can write it as a Hadamard product of 2 one F0 functions, or well, more precisely, one of these factors is a one F0. The other one that depends on C. If C is 1, we get another one F0. If C is greater than 1, then it is up to a simple transformation, a 1 F0, but it is still an algebraic function. So then we can write this 2F1 as the Hadamard product of two algebraic functions, and then it is again a diagonal of a rational function. And the last case that I want to consider here, if C is not an integer, then this 2F1 function has height 1, because we have one parameter in the bottom, the hidden one, that is an integer. But since we have this assumption, we have 0 parameters in the top, so the height is 1. And by Christol's theorem that appeared 3 slides before, this is an algebraic function, and therefore also a diagonal of a rational function. And of course, we can consider the case where A is an n and B is not an integer. Let's proceed. So concluding, 2F1 functions are not very interesting in this context. So we move on to the next complicated case is the 3F2 functions. So now we have 3 top parameters and 2 bottom parameters. And we want to assume, of course, that it is globally bounded, because otherwise, anyway, Christol's conjecture says nothing. And similarly as before, you can consider all the different combinations, but this is tedious and I don't want to go into detail. So I focus on this case. There, all the top parameters are rational numbers, non-integers. Okay, so what can happen now? So in particular, what are examples where we can easily see that it is a diagonal of a rational function? Well, if both of these bottom parameters, D and E, are integers, because then it is similar to the example that I showed you before. We have 3 non-integers in the top and 3 integers in the bottom. So that means this function has height 3, and we can decompose it as the Hadamard product of 3 algebraic functions, and therefore trivially it is the diagonal of a rational function. On the other hand, if D and E are both non-integers, then also it follows easily that this function is a diagonal of a rational function, because by Christol's theorem, it is algebraic because we have height 1. So if these are non-integers, the only integer is the hidden parameter. So we have height 1, and then it is algebraic, and therefore it is a diagonal. Hence, the only case where it is not completely obvious is if one of these 2 parameters, D and E, is an integer, and the other one is a rational number that is not an integer. So let's focus on these cases. Even there, by an argument that comes on the next slide, there are cases where it is relatively simple to show that it is the diagonal of a rational function. So let us now assume that we have D being a non-integer and E an integer, and without loss of generality, we can assume that E is 1. And we assume that this function is globally bounded. So now how can we decompose this as the Hadamard product? Actually,
let me interrupt for a question.
Yes.
So this is a Christol conjecture says if it's D-finite and this condition globally bounded, then it's diagonal,
yes,
of a rational function. Now, the hypergeometric functions you're considering are obviously D-finite.
yes.
So is it known that every hypergeometric function that is globally bounded, the special case that is diagonal, or is it also open?
No. That's why we say it's
so even this special case is still open.
Yeah. Even for, so yeah, of course, there are D-finite functions that are not hypergeometric functions. They, of course, for them we know even less. But even if we focus on hypergeometric functions, we don't know much.
So right now, your immediate goal is to prove the special case for, or disprove for hypergeometric functions?
This is already a very ambitious goal. A less ambitious goal would be to prove it for all 3f2 functions. And the even less ambitious goal would be to prove it for a very particular 3f2 function that I will show you in a minute. There it is still not known.
So it's very challenging.
A very concrete one. Okay, and I'm now just elaborating on how people found such examples. I call them potential counterexamples, because we don't know whether they are really counterexamples, but at least nobody knows how to write these functions as the diagonal of a rational function. So they could be counterexamples.
But
sorry, go ahead.
Can I ask a question? Are there any counterexamples known?
No, because then the conjecture would be settled.
Okay.
So it's actually believed that the conjecture is true, and yeah, no counterexample is known.
Okay, thank you.
Personally, do you believe it's true? So you're looking for a counterexample, or you're looking to prove it?
Well, yeah, of course, yeah. No, I'm a bit indifferent.
Okay.
I don't have a clear opinion on this. From time to time, yeah, I'm hoping to find a counterexample, but I think it's quite hopeless. Okay, so again, we use the Hadamard product, and we try to decompose this 3f2 function as a Hadamard product. And there are several possibilities by combinatorics. So there are two essentially different ones, and then certain permutations. So either we let this one go together with one of the bottom parameter, with one of the top parameters, that gives us this decomposition. So the one of the top parameters, let's say the C, goes here, and the one goes here. Actually, I should here put an empty bracket in this hidden parameter. And the other one that is hidden here goes here, and we have here a 2f1. And of course, we have three other possibilities where we put here either the A or the B. And the second possibility is that here we still have two of the top parameters, but we put a 1 in the bottom. Then there is another 1 hidden here, and we need another 1 here. So, but here we only have 2 1s, so we need to introduce a third one that will be cancelled. So that's why this 1 in the numerator appears here. So here we get a Hadamard product of two f1 functions. And again, there are in total 3 possibilities of this type due to permutation. So this gives us in total 6 ways. Now, if we look at these factors by what we have seen before, we know already that this guy, this is a very simple guy. This is algebraic. So this is a diagonal. And if we look at this guy, this is also a diagonal. This we have seen in the 2f1 slide before. So if we can show that either this guy or one of the 4 other permuted ones is a diagonal, then we would be done, right? So F is a diagonal if one of these 2 is a diagonal. So then there is a theorem that tells us that this guy cannot be an algebraic function and therefore not be a diagonal, because for we had shown that for these functions, algebraic and yeah, so this cannot be a diagonal. So we are left only by focusing on these. So if we want to find interesting examples where it is not immediately clear that it is a diagonal, then we should find examples where all these 3 possibilities that appear here are not algebraic. So if one of those is algebraic, then F is obviously a diagonal. If all 3 are not algebraic, then we don't know. Then it is an interesting example. Okay, so these potential counterexamples, they were constructed in a way that avoids them to be simple Hadamard products of algebraic functions. Okay, and there was a first example that already appeared in this very old paper by Christol, And then 2012 with co-authors Bostan, Boukraa, Hassani, Maillard, they wrote a paper where they gave a list of, I think, 112 of these potential counterexamples where nobody knew whether they are diagonals or not. And so here are two concrete ones. So these two guys, these two 3f2 functions with very simple rational parameters, if you scale them appropriately by introducing here this factor of 3 to the power 6, you cast them into integer series. So they are obviously globally bounded and obviously D-finite, and it was not known whether they can be written as the diagonal of a rational function. Because if you look at these factors that you obtain, so in the first line, you see the 3 factors that arise from the first example. So you see always a subset of the 3 top parameters here. And in the second line, you see the 3 2f1s corresponding to the second example. All of those are not algebraic because those are not globally bounded. Okay, now how can we decide that these are not globally bounded? Let's have a look. Let's look at the first one. Let's expand this as a power series. So, and we have here this Pochhammer symbol. So we have here 2/9 times 11/9, 5/9, 14/9, and so on. So we get arithmetic progressions in steps of 9. And here in the bottom, we get steps of 3. So if we cancel all these factors of 3 that can be put here in the denominator, we get here a arithmetic progression, a product 2, 11, 20, and so on. We get this, and in the denominator, we get this. So now, if it's globally bounded, we must make sure that somehow all the prime factors, except for finitely many that arise in the denominator, get cancelled by something in the numerator. And here we can see that this is not the case. So let's look at this guy. And let's assume k is chosen such that this is a prime number. Well, now it depends. If this prime number is 2 mod 9, then it will appear in this part of the numerator and will get cancelled. Similarly, if it's 5 mod 9, it will appear in this row of factors. But if it is 8 mod 9, then it is not cancelled by anything in the numerator and it survives. And since there are infinitely many prime numbers with this property, we see that this series is not globally bounded. So this was now an ad hoc argument. There is a much more elegant way for deciding global boundedness. Namely, there's a theorem by Christol. And okay, as you see, the theorem is quite complicated, but it can be visualized by a very beautiful picture. So the theorem says, okay, we have these parameters, A1 to AP, B1 up to BP, and the last one is 1. So we assume they are disjoint. These two sets are disjoint modulo Z. We let capital N be their common denominator. So let's look at this example. So here we have 9, 9, 3. So the common denominator is 9. Then this hypergeometric function is globally bounded if for all R between 1 and N, that is co-prime with N. So N is 9. That means we get for R, we get 1, 2, 4, 5, 7, and 8. So we get 6 numbers R. This corresponds to the 6 circles here. So for each of these numbers R, we look at these two sets. We somehow put these numbers on the unit circle. So we take the exponential 2 pi I times R times Bj. And this is, in this set, we have these exponentials for all the B's. And in the red set, we collect all these exponentials for all the A's. And then we draw them on the unit circle. And now we run through the unit circle in counterclockwise direction, and we count how many red and how many blue dots we encounter. And so as long as we encounter more blue numbers than red numbers, we are fine. So here we have blue, blue, red, red. This is okay. Blue, red is okay. Blue, red, blue, red, blue, red, blue, red. This is all fine. But here we get blue, red, red. So at this point, we have seen 2 red bullets and just 1 blue. And this is bad. And this tells us that this function is not globally bounded. Okay. So as you see, it is very easy for a given hypergeometric function to decide whether it is globally bounded or not. You just have to draw these pictures and look. And even more beautiful, a theorem by Boykers and Heckman says that you can even do a similar characterization for algebraic hypergeometric functions. So the P minus 1 hypergeometric function is algebraic if and only if you draw the same pictures, the red and the blue dots alternate, interlace. So if you have this kind of pictures, blue, red, blue, red. So also here we see that this is not algebraic. Okay, so now our theorem, and this is a special case of the main result that I showed you before, is actually these 2 guys. They are special cases of what I had before. And so we proved that they are diagonals of rational functions. And actually, and now here it's the magic behind the thing, we actually guessed this algebraic function, and it was actually Youssef who found it, whose diagonal gives this hypergeometric function. And then by the theorem of Denef and Lipschitz, we know that there is a rational function in 6 variables whose diagonal is this hypergeometric function. And as Doron asked, there is a algorithm that I can quickly show. So this is the general result. Yeah, this is a proof. How can we prove this? Of course, we can do a hand proof by series expansion by using a binomial theorem and geometric series and blah, blah, blah. So this is not interesting. Let me skip this. And we can employ true Vandermonde identity. And of course, then here we can employ Zeilberger's algorithm to find the recurrence and so on and so on. Or we can do creative telescoping on the whole rational function. So, but since time is coming to an end, I also skip this. But this would be the proof that the diagonal of a rational function is D-finite because we can write it as an integral of a rational function. So we can do this simple transformation to our rational function, take the contour integral, and then this gives us the diagonal. And so then by general theory of holonomic functions, it follows that it is D-finite. But okay, this is also not so important. Here you can see how this is done with my package. So we take this rational function, we do creative telescoping, and in the end we get a linear differential operator that annihilates the diagonal. But okay, let me, in the last minute, give you a glimpse of this algorithm by Denef and Lipschitz. So they give an explicit way of constructing a rational function given an algebraic function. Yeah, let me just show how it works. Yeah, no, this is basically here. So it's a step by step. So you do in each step you introduce one more variable, and it's this simple formula. It's not magic, but just since you do this 3 times, the whole expression blows up, and then you get this complicated rational function. Okay, so this one that I showed you before. Okay, so 48 minutes are done. Okay, let me just say this last word. So this is the example that Christol had in his paper. And it looks very similar to the 2 examples that we solved, in particular to the second one. The only difference is that here we have 7/9 and here we have 5/9. So we have solved this one. We have not solved this one. And why can't we get this one? It is because here we see an arithmetic progression. So in this kind of thing, what we do with the algebraic function, we always end up here with an arithmetic progression. And that's why this example somehow falls out. So for this one, still nobody knows. So if you want to get famous, you can try to prove that this function is the diagonal of a rational function.
Let me ask you, do you have any other algorithms that work? I mean, I have a lot of sequences generating functions with integer coefficients. And it would be very nice if there was some general algorithm that might, maybe if you tell, the height, if you make some assumptions, is there any working algorithm that
not that I know of. Yeah, sorry, no, that's unfortunately not that I know of, because if we had such an algorithm for a given sequence to spit out a rational function that generates this sequence as its diagonal coefficients, then this would be the solution of Christol's conjecture. But of course, it would be great if we had such a general algorithm.
But you can't prove that such an algorithm does not exist?
No, I can't prove that. Okay, yes, and so basically this is the end of my talk. So this example is still open. I want to mention that Alin Postan and Sergei Yurkevich, they came up with a generalization of our result, but even their generalization does not include this example. So we have eliminated 2 of these 112 potential counterexamples. They have, with their generalization, they have eliminated another, I don't remember, 16 or so, but there are still many left. In particular, this very original example of Christol still resists all efforts to prove that it is a diagonal. Okay, that's all. Thank you very much. Questions? Doron, I can't hear you. You're not muted, but still I can't hear you. Maybe I stop sharing. Doron?
I can hear you.
I can hear Neil, but I can't hear Doron.
Yeah, I can hear Neil, Christoph, but not Doron.
Yeah, I agree. But if there are any questions, feel free to ask Christoph.
And anyway, we should have a round of applause. So
yes, everyone, please thank the speaker, since Dr. Z didn't get to say it. Are there any questions for Christoph?
Christoph, can I ask you, Christol's original example, it is not balanced, but the problems that you solved, when you add the A's and the B's, they seem to be balanced. Is that changing the nature of the problem? Is that why we cannot get anything about the original conjecture or original example?
That's a good point. I didn't think of that. I mean, I didn't look on whether it's balanced or not. Yeah, no, I don't have an immediate answer to this, but we can tomorrow come to my office. We can look at this.
Tomorrow I'm not in the office, but Tuesday I'll be there.
Are there any other questions for Christoph?
So Doron asks whether my work supports Christol's conjecture by eliminating potential counterexamples. And the answer is yes.
Well, thank you. Very nice talk. Excellent.
Thank you.
Yeah, if there are no other questions, please everyone thank Christoph again for this excellent talk.
Thank you very much. Thanks for inviting me.
Of course. All right. Well, Christoph, I'm sure you're eager to get to bed sometime soon, it being so late. So yeah, thank you, everyone.
I'm so excited now I can't sleep.
Well, thank you, everyone, for coming out, and we will see you again next week for our next seminar.
Sure. See you. Have a good evening.
Of course. Have a good one.
Thank you.